Alrighty, this is lecture number 6 summary about branch prediction. Um, just a quick overview of the branch prediction and what happens is that we need to understand branch prediction and its importance, also as well as the how it can impact the CPI. This is the calculation method that is used, and the different branches that fall underneath it. So just go ahead into this lecture and make this a quick one. Alrighty. So first of all, we just have some objectives that we need to achieve from this. Understanding the branch prediction, the different branch prediction types and methods, and what are their trade-offs. And there we go. First, we have the importance of the branch prediction. What it does is that it keeps the pipeline pretty much with correct instruction sequence, and it also handles like control dependencies. Its main solution is to pretty much like stall pipeline, guess the next fetching address, and have multi-path execution. In this example, it shows like an actual prediction that's taken and an output predicted by a hardware. An output predicted by hardware, it says that it's not taken in all methods when it's actually false. It is taken in a couple, but once it's ran through a branch prediction, it shows that, oh, the actual prediction is at a better percentage error than an output predicted by the hardware. Furthermore, let's talk about the types of branch prediction. They fall under two types. There's a static and there's also a dynamic branch prediction. The static is always not taken, or always taken, or always backward taken, or always forward not taken, which is same as like backward taken. Um uh, As for the dynamic branch prediction, we pretty much it falls into like the last time prediction. Either it's a single bit, maybe a 2-bit counter, or maybe a 2 level, or maybe even a hybrid prediction, which we'll get to later in this lecture about the hybrid prediction. Anyway, the diagram shown to the side is a dynamic branch prediction diagram showing how the prediction or the system itself like pretty much like learns from itself. And in this occasion, it is a 2-bit counter based, and it goes through a cycle, which when it's not taken, it will go to a predict taken, or of a 1-0, and from there will be to go to a not taken, it'll be at a 0-1, and it will just like loop around the whole time. That's how it goes for dynamic branch prediction. It has could be taken or not taken, unlike the static branch prediction. Moving on, we have the branch prediction hardware. The branch prediction hardware falls into 3 categories. There's the branch history table, the branch target buffer, and the misprediction recovery. The BHD pretty much records past branch behavior. The BTB stores target addresses of taking branches, and the misprediction recovery pretty much mechanisms is to handle mispredictions. In the diagram shown, there's a BHD as well as a BTB. The BTB, the branch target buffer, as seen, stores target addresses of taking branches over at the addresses or even the values over there. As for the BHD, it records past branch behavior. As you can see, the um the whole thing starts over here. It gets an address. It's then stored over here at the BTB, and then it leaves the BTB out and then goes through a multiplexer, decodes it or whatever, and then it goes back to the BHD which over there records it. and it can happen over and over again as the BHT at the end of the day uh, addresses recording the past behavior. Excuse me. Nevertheless, let's go to the next slide where we'll talk a bit in depth about the BTB. I said the BTB is pretty much like it stores branch target addresses for quick access, and it also helps reduce branch penalty. And as well as that, it ensures that there is zero cycle jumps for correctly predicted branches. Over here in this diagram, as shown, there is a BTB first level connected to the that in the diagram, as well as a BTB second level, and both of them store branch target addresses, and both also help reduce branch penalty. But one is, excuse me, one is taking information directly from an iCache, and then the other one is taking information directly from a what it looks like a decoder. Anyways, let's hop into the next slide where we'll talk about the calculation of the cost of branches. Always not taken is simple, but it has a low accuracy. The always taken is simple, but it has a better accuracy, which falls into 60 to 70%. Backward taken is predicts loop branches as taken, and profile base uses historical data to predict branch direction. Over here we have an example which shows a static branch prediction and speculation. In this example, if the branch is taken most of the times, and since R7 is not needed on the full through path, we could move add u R7, R8, R9 directly after the 1D instead of keeping them there. If the branch is, however, if the branch is not taken most of the times, and assuming that R4 is not needed on the taking path, we could also move R4, R5, or R6 after the 1D. So it just depends on whether it's a not taken or a taken, and that's how we work pretty much in calculation based on static branch prediction and speculation. Next, we'll talk about dynamic branch prediction methods. There's a last time predictor, like we said, there's a 2-bit counter, there's a global history, and there's a local history predictor. The last time is pretty much like a single bit, a 2-bit is a 2-bit, which adds hysteresis to improve accuracy. The global history predictor uses global branch history to improve prediction. Local history uses local branch history for prediction. Over here we have an example where the prediction is done incorrect and it's done correct. As seen in the incorrect diagram, there's a bubble left because of the avoiding of using the LW in that case, and just like jumping into an OR example with 7, 8, or 9 instead of just sticking to the 1, 2, or 40, and which caused a bubble and then a 400 PS instead of a 200 PS, which is a more delay or stall in this occasion, which caused the prediction to be incorrect. However, when done correct, the prediction has less stall and runs smoother with better accuracy and efficiency. Next here, we'll talk about the hybrid branch predictors, which is going to pretty much like sum up our whole slide lecture today. It combines multiple prediction algorithms, and an example of it is pretty much a hybrid of 2-bit counters. And the benefits behind it is that it gives better accuracy and reduces warm-up time. Over here, we have a branch adder and a history regulator as well. And as seen, it's connected to a tagless 2K BTB and a tagless 2K BTB, and both of them are predicting our target at a better accuracy and reduced warm-up time. Last but not least, here's just a summary to see and take away from today's lecture. The importance of branch prediction is that it's essential for keeping the pipeline full. The types of it are static and dynamic, as we discussed. The branch prediction hardware has three types, which are the BHD, the BTB, and the recovery mechanisms. And we talked about the static methods, which were always not taken or always taken, or before the sorry, we said always taken, always not taken, and backward taken or forward not taken. The profile based, and we also talked about the dynamic methods, which are the last time 2-bit counter, global and local history producers. And as for the hybrid predictors, we talked about how like combining algorithms can be better for accuracy, as explained in the last slide, where we use two branch target buffers, BTBs, to reduce stall and for better accuracy. The whole summarization behind this presentation is that it provides a comprehensive overview of the branch prediction, including its importance, its types, hardwares, and dynamic methods, which fall also into hybrid predictors. And it just gives us a direct image of what branch prediction falls into. Anyways, this was today's summary about lecture number 6, which covered branch prediction and its types. Thank you so much and have a good day.